Let me make it towards the whiteboard. I was just telling you, no, all of you can hear me, right? Just let me know. So I was telling you that last time we talked about the differential and what is differential. When at this moment you all know the differential is change in rate in one variable with respect to the change in rate in another variable, right? So this is the in change of rate of change of variable x, variable y with the rate of change with variable x. And here we have this phenomena that this change should tend to 0. And based on this theorem, then we see the different rules. Yeah, different rules of differentiation. The measures are that dy by dx of a constant, dy by dx, like differential of a constant, differential of a linear function, what are the differential of quadratic function, power function. Then we talked about the root function, additive function, subtractive function. Then we also talk about the product rule of two different subvariables, division of two subfunctions, log function and exponential function. So we talked all, and we also proved this based on this measure formula. That's what we did yesterday. After that, we also saw some how many derivatives we can take it dependent on us. That is known as order. Like with order 2, with order 3, with order 4, and that's how you can hear me, guys, right? So we can talk about different orders. So that's what we did. Then we talked about chain rule. Now, what is chain rule and how it works? How we take differential of chain rule. So I'll quickly overview the last lesson. Um, then we talked about the partial differential, right? With respect, what is partial differential means? If y is a function of different variables, x1, x2, and so on, xn. So if I want to take the differential dy by dx 1, so I will consider this as a variable and rest as a constant. So rest will be 0, so I will just differentiate this function and not the rest of it. Right? Then we talked about the first order condition and the second order condition of optimization. Sorry. First order condition, it usually gives us the optimal values for our variable x. That's we just put, what is first order condition? We just put dy by dx equal to 0, and we get the optimum value of x, x1 and x2, and we say this is the optimum value for our function y equal f of x. And the second order condition means that this second derivative, like this one, this should be minimum. It should be greater than 0. If these two conditions satisfied, then we call it our function is optimal function. So we just should choose that point. Today we are going to and we didn't talk much about integration because there's not so much use in this course of integration. But remember, integration is shown by this sign, and it's an antiderivative. Means it's an opposite of the derivation. So, for example, x cubed by 3. So integration of this will be 3 will come here, and x squared will be x squared, right? So which is actually antiderivative of this function. Usually the main thing is like you put, if for example, if x of n and you want to do integration, so you can get x n plus 1. In derivation, we use n minus 1 and divide by n plus 1. So that's an integration. Integration always have limit, but we are not gonna go deep in this integration because we're not gonna use it. So just stick to the differential, and next today what we're gonna learn about matrices. Matrix. Maybe when you see this word, the movie comes in your mind. There was some movie with some serials, Matrix, right? What is matrix? That we're gonna talk about today. It's really an important concept of a calculus in economics. It basically is a calculus concept in economics and finance. Finance, especially when we talk about portfolio. Okay? To get an expert analysis and to concluding the evidence using data, we use matrices. Basically, matrix is a set of a data, and the plural is matrices. So we will talk now about different features and operation of matrix. Then at the end, we will also give 10 to 15 minutes to initiate the reviews. So when we talk about matrices, remember any single number, any number, 1, 2, 3, 4, right? Any single number is also known as scalar because it is scaled somewhere. Oh, sorry. I forgot. Thanks for suggesting. Yeah, before we were just overviewing. So right now we are talking about matrix. So remember, any single number is also known as scalar because we need to scale that number. It can be any integer, even it can be a decimal. For example, 0.450, that's also a scalar, right? 0.49. It can be integer, it can be into decimal, it can be negative, it can be positive. So that can be negative, that can be positive. So all these are scalar. Whereas matrix, so this is a single number, right? Is a scalar. Remember, when we talk, so what I'm gonna do, I'm just gonna write and rub it because we don't have time. So you can just have a look and just get it. So that's about the single number. What is matrix? What is matrix? Matrix is a set of numbers, right? So now you know scalar. It can be integer, whereas a vector is one-dimensional. What is vector? Vector can be a set of two numbers, this one, and it is one-dimensional. There can be any number here, a11, a12, any number. So this is one vector, right? Array, right? So it is unidirectional. We can also call it array of numbers. For example, 2, 3. Now this is a vector. It can be in a row form, in a column form, right? So this can be vector. And so now you know scalar, now you know vector. Scalar is just number, any number, right? So this is a scalar. Let's say 2. What is matrix? Matrix is at least minimum two-dimensional. means 2. So this vector can also be considered as a matrix. Two-dimensional, at least, collection of array of numbers, right? So here, one thing you can say that what is array? Array is like to arrange the numbers into column or row. That's array, right? Just like this, A11, A12. Hence, matrix contains at least one of two, that is either two rows. So here in matrices, we define rows as R, columns as C. So we know that matrix is two-dimensional collection of arrays. So it means at least our matrix should contain either two rows or two columns, right? So either it can be this one, two rows, this is two rows, or two columns. Then it's a matrix. Whereas one is just a singular, a scalar thing. We in financial use, we use in financial economics, we use or financial analysis, we use matrix for what? To conduct portfolio. All right, portfolio, you already know portfolio. Portfolio means like investment in smaller part to maintain at least a sustainable return. So this you understand, right? How we do it in a portfolio, I think next week we're gonna talk about the portfolio management. That how we're gonna use matrix in portfolio. But usually we have different sets of investment that we put that data into matrix, right? Now, it mostly solves the economic problem when we have a system of equations. System of what kind of equations? Linear equations. Like let's say this is one a1 y1 a b x1, then y2 equal to a plus b x2. So I can write this one y as a y1 y2 equal a1 a sorry a b, and let's say this is c. This is another equation, and d, c, d, and this is x1, x2. So with this, by using matrix, we can also calculate x1 and x2, and y1 and y2, and a, b, c, d. How? For that, we need to know different rules, different properties of matrix, right? That's what we're gonna do right now. Okay, La? But we can use in economics and in finance a lot this matrix. Mostly matrix can be denoted by any letter, but usually we use A or M. But you can also use B, C, D, E, F, G, means any letter. But remember to give a notation with a capital alphabet. What are the dimensions? So dimension means how many rows and how many columns. So mostly it is denoted by R times C. Rows, that is rows into column. we can also denote it by small r and small c when we are talking about matrix. For example, I can say A is a matrix with many outcomes, with many like A11, A12, so on, A1n, A21, so on, A1, here A2n, A n, so on. So this is a matrix. What is the dimension? N by n matrix. So it means there are n rows and n columns, right? N rows, see, and n columns. Yeah. And it is denoted by A. That's what I told you before. Then what is a row vector? So next topic will be within matrix. While defining the matrix, you should know some. What is row vector? Can you guess? Any vector which only has one row, that's a row vector, as it is shown by its name. So row vector. So this is A11, A12, A13, so on, A1n. This is one row vector, right? It can be only with two, it can be up to n. So what is the dimension of this matrix? One row, n. So row vector is always 1 by n. And here means any kind of column. I mean, it can be one column, two column. Similarly, we have column vector. So what is the column vector? It should be n times 1. That's the dimension I'm telling you. Okay, so column vector will be the transpose of the row vector. Transpose means the rows, the change of row into column and column into row. Okay, so A11, A21, so on, A n1. So remember, this is row, this is column. So in Aij, I is showing the row, number of row, and J is showing the number of column. Okay. Then we have, now you know the row and you know the column. So then we have a square matrix. Square matrix means equal number of rows and equal number of column. For example, n by n in my previous matrix is like a square matrix. This is a square matrix. A11, A12, A21, A22. Remember, you can put any number. For example, 3, 4, 2, 1. This is a square matrix because it has 2 by 2. 2 rows, 2 columns, right? So when the number of rows and number of columns are equal, that we call square matrix. So you should be familiar with these names and you should know the main features. That if I ask you write down the square matrix, so you should write in such a way that, right? If I ask you write down a vector matrix, or there is a vector matrix, so this thing come in your mind for column vector, and for row vector, this should come into your mind. So that's why I'm telling you these concepts. If all the numbers are zero, then it's known as zero matrix. So what is zero matrix? Mostly it's easy because you can see it from its name, right? Zero matrix, 0, 0, 0, 0, 0. This is zero matrix, right? It can be. This is also zero matrix, zero vector map, right? So it can be any number. So that's, you know, the zero matrix. Then there is symmetric matrix. If the diagonal is drawn and we get equal half, means the number of rows and number of column will be divided equally in two equal halves. That's a zero matrix. For example, if I have this one, P F G H I J K L. Oh no, sorry. A E I O and so on. If you want to extend it, I just take it by 4 by 4 matrix. So then whatever here, if the rows and columns are exactly the transpose here of between the diagonals, like on the two sides of the diagonals, then it is like a symmetrical matrix. For example, B, here we have B, C, and D. And here we have F and G. And here we have H. So what should be here? B should be here, C should be here, and D should be here. So whatever row here is a column here, right? After, like, not including the first number of the matrix. Do you understand? And similarly, we can have what should be here? Here should be F and G. And what should be here? H. So if I see these diagonals, so this half is exactly the same as this half. So that's why we call it symmetric matrix. You know the symmetric shape, right? You cut it and you have to do two equal halves. If you want to see numerically with the numbers, let's say 3 minus 1, 2, 9. Right? And here we have 4, 3, 7, 6, 5, 8. So here should be 4, 3, 7, 6, 5, 8. So this is a symmetric matrix. So now if any matrix you can see, and if you can see such way, then you should know that it's a symmetric matrix. The diagonal is very important in symmetric matrix. Right? Now, what is a diagonal matrix? A diagonal matrix, for example, you have some number a, 2, 2, and so on, a and n, and rest numbers are 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Oops. So on, so on. So rest numbers, except from the diagonal, every other number is 0. That's a diagonal matrix, right? So if we take a numerical example, so I can say that A is a diagonal matrix if we have 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is a diagonal matrix. So here on the diagonal, we have numbers, but other than diagonal, there are no numbers. Similarly, if all the numbers are 1, if we have this 1, 1, 1, 0, 0, 0, 0, 0, 0. So mostly some students, you should write actually rows and columns here. So I'm not writing it because it's understood, because I have to make matrices again and again. So this one is we call it identity matrix. What is the beauty of identity matrix? If you multiply identity matrix with any matrix, it will give you the same matrix, okay? Just like multiplying any number with 1, it gives you the same number. So that's known as identity matrix. So let's take a couple of minutes break, and when we come back after 5 minutes, we will talk about how to add and subtract. So these are some matrices you should know, right? And we will also talk about the singular matrix. What is singular matrix? So let's have a 5 minutes break, then we will continue.